let's look at this question here. It was the first question of JEB mock paper 2026, and it says electrochemical cells generate energy from spontaneous redox reactions. Their importance lies in driving modern technology through energy storage, industrial manufacturing, etc. A group of senior 5 students under their science club have undertaken a project to select the strongest oxidizing and reducing agent between copper and zinc. It is an electrochemical cell made up of electrodes, copper and zinc, and they want to select which one is the strongest oxidizing and the strongest reducing agent. And they also want to construct an electrochemical cell and apply quantitative chemical principles to make recommendations, but they could not proceed. And when they consulted their teacher, he provided them with the following thermochemical and electrochemical data. And here is our electrochemical data. This is our electrochemical data that we have been given. And thermochemical data is above, then down we have electrochemical data. So what I want, these 5 students are now challenged and have approached you. Task as a chemistry student, analyze and interpret the data to address the issue. In this question here, I managed to highlight the most important areas which I think a learner should put emphasis on when planning to answer this question. So I'll go straight to the answering. So what will happen? So if I want to identify which one is strongest oxidizing and which one is strongest reducing, then I must be knowing that in an electrochemical cell, I must have, for example, copper when it is in gaseous state. For me, the copper I'm going to use is the copper 2 ions, which will be in solution, and the 2, when I put copper to copper 2 ions, it loses 2 electrons. This electrochemical cell is going to be a play between zinc ions and copper 2 ions. So copper gas, when it goes to copper 2 ions, it releases 2 electrons. So what will be the energy change if copper gives me copper 2 ions? That is what I'm going to look for. In order for this copper to give me copper 2 ions in aqueous state, I will first apply the first ionization energy. And when I apply the first ionization energy, it will give me copper plus gas. Then to it, I apply the second ionization energy. And when I apply the second ionization energy, I get copper 2 plus gas. Then after that, I will apply the hydration energy, enthalpy of hydration, in order for me to complete this process. So, first ionization energy, when you look at the data I have been given, it is equal to 754 kilojoules per mole. And second ionization energy of copper I have been given 2100 kilojoules per mole. And the enthalpy of hydration of copper, the second ionization energy is, let me collect here. Okay, the second ionization energy of copper is 1958 kilojoules per mole. And then the enthalpy of hydration is equal to 2100 kilojoules per watt per mole. Then what I need is the enthalpy change of this process, which I'm going to call the H change. I'm denoting it to the HC. So we know that when you have a diagram which resembles a Born-Haber cycle, the clockwise direction, this is now clockwise. If I try to move like this, it is clockwise, is equal to the anti-clockwise. direction. So what would that mean? The only arrow which is going clockwise is the arrow where I have the HC, and the rest are going anti-clockwise, and we are saying clockwise is equal to anti-clockwise. Therefore, HC is equal to first ionization energy plus second ionization energy plus the H hydration. Therefore, when I put in enthalpy change for this overall process will equal to 754 plus second ionization energy, which is 1958, then plus, but remember this is hydration energy, and hydration energy is an exothermic process, so I'm going to introduce a negative here so that this one becomes negative 2100. The answer I get will be in kilojoules per mole. So when you use your calculator, you get the HC equal to 754 plus 1958 minus 2100. I get positive, this is positive 612 kilojoules per mole. So that is the enthalpy change if I use copper if I use copper as an electrode in what? In an electrochemical cell. That is the enthalpy change. I will be needing 612 kilojoules per mole for copper to be giving me copper 2 ions. Alright. Then I'll switch and go to zinc. I'll switch and go to zinc. If I switch and go to zinc, I'm going to separate here and try out for zinc. What will happen for zinc? The same case happens for zinc. If I have zinc gas and I apply a certain energy here, then I'll get zinc 2 plus, then plus 2 electrons. This is aqueous. So what will happen to zinc? I'll have to first apply the first ionization energy, which gives me zinc gas, and after that I will apply the second ionization energy, which gives me zinc 2 plus gas. Then I apply hydration energy of zinc in order to get the zinc 2 ions, but in aqueous state, because in electrochemical cells the ions will appear in aqueous state and not in gaseous state. So for this case, this enthalpy here is my enthalpy change, which I'm now going to call the HC1. I'm denoting it the HC1 to the enthalpy change for the overall process. But I have been given first ionization energy of zinc. You can come here and check. First ionization energy of zinc is 906. So 906, I come here and put this one is equal to 906 kilojoules per mole. Then I have been given, I have been given second ionization energy of zinc, which is 1733.3. So this enthalpy change here is equal to 1733.3. Then I have been given hydration energy of zinc. You can look here, it is 2046. So I'll come and put here, this is equal to 2046 kilojoules per mole. All energies are in kilojoules per mole. So if I apply the same principle I applied last time, clockwise equal to anti-clockwise, it will mean enthalpy change for this process is equal to first ionization energy of zinc plus second ionization energy of zinc plus the H hydration of zinc. But just as last time, the enthalpy of hydration, I have to introduce a negative because we know the process of hydration is exothermic. It cannot be endothermic. Hydration can never be endothermic. Even when enthalpy of solution is endothermic, hydration energy remains exothermic. Therefore, the HC1 is equal to 906 plus 906 plus 1733.3 minus 2046. When you punch that one in a calculator, you get the enthalpy change for the process as this is 906 plus 1733.3 minus 2046. You get the answer, which is positive 593.3 kilojoules per mole. So now I compare the two answers because data interpretation is a must. Now after getting these two answers, I'm going to compare. When I'm using copper and zinc, copper needs 612 kilojoules per mole to give me copper to ions, and zinc needs positive 593.3 kilojoules per mole to give me zinc to ions. So this one implies that it is easy for zinc to give out electrons compared to what? Compared to copper, because copper is needing more energy. And since it is easier for zinc to give me electrons, it means that oxidation will take place at the zinc electrode. I repeat, oxidation will take place at the zinc electrode since zinc requires less energy to give me electrons. And if oxidation takes place at the zinc electrode, it means that zinc is the most reducing agent. So I will say, I'll come here and interpret and say, since the HC1 is less than the HC, this implies that zinc easily lose electrons compared to copper, and therefore in the electrochemical cell zinc will act as the reducing agent. Zinc will act as the reducing agent, and copper will act as the oxidizing agent. So that is my data interpretation for part 1. But the question does not end there. The question continues. And decide when you see where I put the green line in the question, they need to construct an electrochemical cell. And if they need to construct the electrochemical cell, then they need to know what is the anode and what is the cathode. But in my data here, I have been given oxidation potentials, zinc to zinc 2 ions and copper to copper 2 ions. Those are oxidation potentials, but we all know that it is very easy to analyze data using the reduction potential. So I'm going to rewrite these equations in order to come up with the reduction potentials. So this is what I've been given. So I've been given zinc to zinc 2 ions, but I'm going to write the equation. This is for zinc, reduction potential for zinc. For reduction potential of zinc, it will be zinc 2 ions, aqueous, adding it 2 electrons in order to give me zinc solid. But since above here I have been given the oxidation potential, to get the reduction potential, I just reverse the sign on the oxidation potential. So here E reduction is equal to negative 0.76 volts. Then I go to copper. Even copper, I was given oxidation potential. So for copper, it will be copper 2 plus 2 electrons. This is aqueous, plus 2 electron to give me copper solid. And also I reverse the sign. So it means that E reduction or reduction potential is equal to, I reverse the sign, so this become positive 3.4. Sorry, it is positive 0.34 volts. Now after getting the reduction potentials, my next thing I'll do here is to determine the EMF of the cell. And we know that EMF of the cell, okay, before that you can interpret the data. Because you have got the reduction potentials, you are capable of interpreting the data. When interpreting the data, the element or the electrode with a more negative reduction potential acts as the anode, and the one with a more positive reduction potential acts as the cathode. Therefore, here I'm going to say zinc is the anode. Then I have to give a reason why. Because it has a more negative reduction potential. Then I go to what? I go to copper. If zinc is the anode, then it means that copper is the cathode, because it has a more positive reduction what? Reduction potential. Or you can say less negative. All are right, because at times you will find that both values are negative, just that one is more negative than the other. So it depends on what you have found. Okay. Then after that, since I have identified the anode and the cathode, then I can write the overall equation. If I construct this cell, what will be my overall equation? If I construct this cell to write the overall equation, since zinc is the anode, for it will be giving out electrons. We know electrons flow from the anode going to the what? Going to the cathode. So zinc will be giving out electrons, and the equation will be zinc, which is a solid, will be giving out electrons to form zinc 2 plus aqueous, then plus 2 electrons. Since zinc is the anode, that is what will happen. And since copper is the cathode, for it will be accepting electrons, and the equation will remain. So this is copper 2 plus aqueous will be accepting electrons which are coming from zinc to form me copper solid. So what happens is that if I want to write the overall equation, these electrons can cancel out, so that my overall equation will become zinc solid plus copper 2 plus aqueous, then to give me zinc 2 plus aqueous plus copper solid. So that is my overall equation, which will be happening in the electrochemical cell I'm trying to construct. And in this electrochemical cell, the cell notation will be zinc solid. Since I'm separating a solid with aqueous, I'll put a slash, and this is copper 2 plus aqueous. But in this electrochemical cell, I'll need a salt partition or a salt bridge in order to allow free ion exchange between the two half cells. So this side I'll have zinc 2 plus aqueous separated from copper solid. So the half cells, I have got them. Now I need to find out what will be the EMF in between these two cells. I know EMF in between these two electrodes. I know EMF is equal to E, electrode potential of the what? Of the cathode, minus electrode potential or reduction potential of the what? Of the anode. At times you can find another box saying, or EMF is given by E right minus E left. But you have to make sure that the potential you use is reduction potential for this formula. If you use oxidation potentials, the answers will be wrong, and I have already talked about how you obtain reduction potentials from oxidation potentials. So what will happen? What is my EMF? EMF is equal to E right, or my cathode was copper, and copper I have 0.34. So I'll come here and put 0.34 minus, what is my anode? My anode is zinc, and it has a reduction potential of negative 0.76. So this is negative 0.76. The answer will be in volts. So EMF of this cell is equal to, if I use my calculator here, 0.34 plus 0.76 gives me an answer of 1.1 V. So that is the EMF that will be in between the electrodes when arranged in an electrochemical cell. Now if this is the EMF, remember when EMF of the cell is positive, it means that the cell is feasible. It can operate spontaneously without addition of energy. Why? Because a positive EMF gives me a negative Gibbs free energy. We get Gibbs free energy by the formula of negative Fe, whereby these are number of electrons exchanged, and this one is the Faraday constant, which is equal to 96500 coulombs, and this one refers to the EMF. So I have everything here, and I know in this cell I was moving 2 electrons from zinc and taking them to copper. So number of electrons are equal to 2, and EM of the cell is 1.1 V, I have calculated. So if I try to get the G, or Gibbs free energy, the G is equal to negative 2 times 96500 times 1.1. So my Gibbs free energy for this cell is equal to negative 2 times 96500 times 1.1. So I get negative 212,300. These are joules, but I can convert them to kilojoules by dividing with 1000. Therefore, the G is equal to negative 212.3 kilojoules. I'm not saying when you present your answer in joules it is wrong. No, we usually prefer kilojoules because they summarize. It's like having a lot of money, and instead of counting them in Ugandan shillings, you start counting them in dollars, because dollars are a bigger value. They make a smaller digit and easier to manage. Therefore, this is my DG, Gibbs free energy, and since Gibbs free energy is negative, it means that this cell is spontaneous, and that's why I was saying that this cell is feasible. It does not need us to add energy, because the cell operates by giving out what? By giving out energy. So I will interpret that and say, since the cell has a positive EMF, comma, it gives it an or I can say it is fissile. If the cell has a positive EMF, then the cell is fissile. Since it will have an exothermic, keeps free energy. Alright, so it gives it an exothermic, gives free energy, meaning the cell is fissile. So by talking about constructing the cell, that one I have discussed is enough to mean constructing the cell. I have identified the anode, I have identified the cathode, I have identified the half inclusions at each electrode, and I have the cell notation plus communicating that this cell is fissile. But if you still have time in the exam, you can put a diagram to mean the cell you are constructing. So the cell I'm constructing is this. I have this electrode here, and I have another electrode. And when you look at my cell notation, there is a porous partition here. So this one, I'm going to link them together by a porous partition to allow free exchange of ions between the two half cells. Then here I have an electrolyte, and equally I have to have an electrolyte here. Each half cell has to be with its own electrolyte. Then this cell will operate when the two are connected together. Now next is naming. So I'm saying this one is a porous partition. Actually, the way I have drawn it, it better suits a salt bridge than a porous partition. So this one is a salt bridge. Then I got my diagram. Which electrode is on my left? The electrode on my left is always the anode, and my anode was zinc. So I come here and say this one is zinc. Then the electrode on the right is always the cathode, and my cathode was copper. So this is copper electrode. Then after that, if this is zinc, then we immerse it in an electrolyte containing zinc. In most cases, we use zinc 2 sulfate. What we are constructing is a Daniel's cell, and standard Daniel's cell has zinc sulfate as the reactant, as the electrolyte where we have the zinc electrode, and where we have copper, we have copper 2 sulfate electrolyte. Then we have calculated and obtained that the EMF that will be between these two electrodes is 1.1 watt, 1.1 V. Then this one is just a cable connecting a cable, because this is flow of electricity and we need the cables in between. So if I'm to predict flow of electrons, we are saying electrons flow from the anode as they are going to the cathode. So this is flow of electrons. They flow from the anode going to the cathode as current flow from cathode going to the what? To the anode. So that is flow of electrons. So this is my cell here, and we are saying the cell is fissile because of this positive EMF it has. Then I go back to the question and check anything I have not yet answered. Okay, The students were challenged. Now we need to look, they are going to apply quantitative chemical principles. So I now have to discuss any application of this cell in their life. An application of this cell in their life. So here I'm going to discuss applications of the cell. One application of the cell is that it converts chemical energy into electrical energy that can be used to run machines. Converts chemical energy into electrical energy that can be used to run machines and maybe domestic cooking. Can be used to run machines and in domestic cooking. That is one. Another one I can think of is the study of corrosion, because you know this involves dissolving of electrodes, and therefore we can use it to study corrosion. The cell can be used to study corrosion of different metals. So those are my applications of this cell. Maybe I go back to the question and find out if there is anything else I have not included and it is needed according to the question. This is my question here. Applications are there. Apply, recommendation, that cannot proceed. Yeah. Maybe a recommendation. Never know the marking aid. The examiner can say, this student, after doing all that, he has to recommend. Should we use the cell or not? So recommendation here. Examiner may have interests in the recommendation. So according to you, should we use this cell or not? This cell, we are free to use it because we have already seen that the cell is feasible. So I will say, I advise the senior fives to use the cell because it is feasible and operates spontaneously. So they will not need to apply energy in form of electricity because this cell will be operating spontaneously. Now let's look at scoring. How will they score such a question? Let me see. Before I got scoring, is there anything I'm leaving out? To consult their chemical. Yeah, I've answered all the necessary areas of the question. So if it is scoring, how will they score this question? Analyzing this data here will be scored and it will be given data analysis. That is data analysis. Then when you come here, this one, you wrote this statement when you were applying a law, and this is data analysis. And the final answer can also take data analysis. Then you didn't just get the answer, but you interpreted this answer, so you get data interpretation, which I denote as DI. Then I come here, you were analyzing data, you stated this law, and you got data analysis here. Then I continue down. When I continue, actually from there we came here, where we managed to identify the electrodes. So in identifying the electrodes, you managed to write the halving equation. The halving equations, but those are not the halving equations I'm going to mark. I'm going to score these ones. These are halving equations that I'm going to score, the ones which gave us the overall equation. The other one for obtaining reduction potential, not mark. But this one here, is data interpretation, because you identify that one who has a more positive reduction potential, and you told me this statement, so that is data interpretation. This one, cell notation, I will award it like an equation. Then this one is a law you are applying. Then after applying that law, you manage to analyze data. So this is data analyzed. I give the final answer, data analyzed. Then when you go to Gibbs free energy, you stated the law first. I give this one as a law. I come here and give data analysis marks. Then I continue. After doing that, you interpreted this data, so I give you the I, data interpretation. Now for this case here, because you can make this conclusion by just having EMF, I will score 1. Either I score EMF or I come and score data I score Gibbs free energy, but I will not score both. I score for EMF and I score Gibbs free energy. That is a repetition. You are applying the same, you are looking for the same thing of concluding whether the cell is feasible or not. So a person who look for Gibbs free energy, I will score, but those scores I will not count them. I come to this diagram. This diagram I have already scored this side, but assuming someone didn't have this information this side but came straight to the diagram, then I'll come here and score that this is data analysis and score the whole diagram. But this person who draws the diagram, I'll give you fewer scores. If you draw the diagram and you don't write this information which is here, then I'll score you a maximum of 1 score in total, because we don't have scores for diagram on the marking rubric. So I will just sympathize with you and give you some marks. You are giving an application and you are explaining it, that one gives you EA. Then I come to the recommendation. The recommendation, we don't have scores on the rubric for recommendation. So unless the examiner has interest in it, that is when it can be scored. So after scoring like that, I'll come and count how many DI are there. Assuming there are 6, then I say student who brings 6 DI as DA and interprets twice, maybe 6 DI, that student should get a score of 3. Then how many laws are there? In my work I have applied 3 laws, but I say the 2 laws are after one thing. So I'll say student who bring at least 2 laws gets a score of 0, 2. Then I go back. What else is in this work? Application is a student who bring 2 application will get a score of 0, 2. So what is the total? 3 plus 4 gives me a total of 7. And this question will be out of what? Out of 7. Thank you for watching. Subscribe.